Because the mixture was uniform, it is 0.01 divided by 2, and this gives us 0.005 moles all in 500. So if we fetch a solution that has 0.005 moles in 500 centimeters cubic, has the same concentration as this. In other words, if we take half of this, then it is going to have in itself 0.005. If we now fetch 250 of it, 250 centimeters cubic of that would have this number of moles present. Divide by 2, giving us 0.0025 moles. In other words, if you have 0.025 moles in 2, it has the same concentration as 1,000 of 0.01 moles. Because what we have simply done is saying that we have simply taken from the 1,000, after mixing and stirring, taking it and fetching from it. We are saying, for instance, we have that solution in that beaker. It is 1,000 centimeters cubic. If you take 500 from it, the concentration does not change. And you take 500 and you put there. What we are saying is here we have 0.01 moles in 1,000. So in 500, it is this divided by 2. And the moles here in 500 will be 0.005. That means solution, this one and this one, have the same concentration. If we now fetch from here, and we fetch another one that is 250 mLs from here now, what that one means, from here we had 0.005. So the 250 mLs from here will carry half of that, and that is 0.0025 moles into 50. What that one means is simple, that solution 1, solution 2, and solution 3 have the same concentrations. These three have the same concentrations per liter. This is 0.01 moles per liter. This is 0.005 moles in 500, and therefore in 1 liter it will be 0.051. This is 0.0025 moles per 250 centimeter cubic, and therefore in 1 liter. Then these three solutions have the same concentration, but these two have different. Kwa nini? Because we are saying this one is in 1,000, this is in 1,000. But when you take differently, then that is what we are going to get. Now, we can still look at a liquid, for instance. A liquid, say, sulfuric acid. This acid will be sold as a liquid, cannot be sold as grams. But we know then we can use another concept of density to get the mass. So this acid here, concentrated sulfuric acid, has a mass that is RAM, relative formula mass, of 2 for hydrogen, 32 for sulfur, and 64 for oxygen. That giving us a total of 98. So when we take 98 grams of this, then this will be the formula mass, and that is the one we are going to use. So when we are dealing with this acid as sold, it has a density of 1.84 grams per centimeters cubic. What does that one tell us? That we have, for every 1 centimeters cubic of the acid, it has a mass of 1.84 grams. And remember, this is not pure. This is impure because it contains other chemicals in it. However, ignoring the impurities, we can ask ourselves, what about 1,000 centimeters cubic, which is equivalent to 1 liter, which is equivalent to dl cubic, will contain how much? This will be 1.84 times 1,000, all this divided by 1. This one giving us 1840 grams per 1,000 or per 1 liter. So this is the concentration. This is the concentration of that acid. So if we know, note that given that the acid is 98% pure. If the acid is 98% pure, that one gives me an opportunity to say, if this is the concentration of the pure acid, so the concentration of pure acid will be 1840 multiplied by 98% of that. Take 1 minute of your lesson and work it out, as I work it out as well. This is 1840 divided by 98, giving us, according to mine, 18.775 grams per liter. And that is sorry. This is 1840 times 98 divided by 100. 18, sorry, this is not the answer. It is 1803.2 grams per liter. That is the concentration. That is the concentration of that acid. So we can convert into moles per liter. So this is 1803.2 now divided by 98, which is the lamb. And let us see what this one gives us. This gives us 18.4 molar sulfuric acid. So the acid, as we buy it from the shops, we will be given the density on its label. That density tells us it is grams per centimeter cubic. Now this is what we get. That tells us we can work out in centimeters cubic, which is in 1,000, which is 1 liter. So we're going to get 1840. Now if we know the percentage purity, which will be written on the acid label as acid. So the acid will be given as something 98%. That tells us the acid is 98% pure. So the rest is not is impurity. So once we work it out, this times this, then we get that amount. This is the concentration in grams per liter. And therefore we can change it into moles per liter. How do we make a solution from an acid? Now we have already noted that this is 18.4 molar sulfuric acid. How do we prepare a less concentrated acid? We can only do that by using water. In the case of sodium hydroxide, we took the pellets We took the pellets and we added to water, and from here we did the activity of doing the stirring and we got a solution. Now note, here there are two options. You add the water to acid, or you add acid to water. Now these two exercises are different. During preparation, if you add this reaction of an acid and water is highly exothermic and explosive. This reaction produces a lot of heat. So if you add water to acid or acid to water, the amount of acid heat produced is different. The acid, you're adding water to a lot of acid. And in this case, you're adding acid to a lot of water. So you find that in this case, this is a very dangerous move. Dangerous. This is like swimming in a swimming pool, highly vested by crocodiles. This is dangerous. Never try this in school. You always add acid to water. You add acid to water when you are making this solution. Now from there, class, we move on to the next item of dilution. Dilution of solutions. Now you certainly realize, where do we dilute? When you have visitors at home and you have some juice, you would add water depending with the number of people who have visited, so that the same amount of juice would be enough. Or when you are those of your parents who take some alcoholic beverages, they add water to the alcohol to get a less. This one we are going to do to get a less concentrated solution. Now in this case, we want to take an exercise here. And this exercise, I want you to be very, very keen. This is juice. And this is the other. I want to assume that I have two sets of Kenyans. I want to assume the two are equal. So in the two glasses, I have, assuming I have Kenyan one Kenyan, and I have a Kenyan number 2. This is myself, and this is my partner here, Mheshimiwa. Now here, I have put equal amount of juice. So this juice is about 25 ml each. So I'm saying here I put 25 ml of juice. And here I give Babu 25 ml of juice. So in this case, you discover some of these Kenyans, like Babu, they love taking hot. You take hot. People like us would add some water. And when we add some water, then we would stir to mix. Remember, the amount of juice here has not changed. And the amount of juice taken by Babu here is 25 ml of pure juice. The amount of juice that I've taken is 25 ml. But in mine, I've added water because it's too hot. So in other words, I have taken a less concentrated juice, while Babu has taken a very concentrated juice. So in this case, this is the exercise of diluting. Now, what are we going to do with this dilution? We are going to take 40 grams of sodium hydroxide in 1 liter, which makes it 1 molar sodium hydroxide. This is the solution I want to make. But now from here we can dilute this. We can dilute here. How do we dilute this one? We simply dilute by adding water. By adding water. Just like in the case of the juice that I've taken and the juice that will be taken by Babu. In this case, let us see the mathematics that goes along with that. 1 molar sodium hydroxide. And I want from here to dilute it to 0.002 molar sodium hydroxide for about 500 centimeters of solution. So we want to see, assuming this is the juice that is concentrated 1 molar, which is 1 moles per liter, and I want to make 0.002 moles per liter, and I want to make 500 centimeters cubic. How much of this, the one that Babu took, will I need to make this amount of solution? Now in this case, this is what we do. We are saying here that 1 mole is in 1,000 centimeters cubic. And here we are saying this is 0.002 moles in 1,000 of the diluted solution. What about 500? I'm going to say 500 times 0.002 divided by 1,000. 1, 2, this is 1,000. This is how much? This is 1,000. So this is 0.1. This is 0.1 moles. Let me confirm. So that one doesn't give me trouble. 0.002 times 500 divided by 1,000. This is 0.001. Those are the moles that I need to fetch from this Babu's solution. And I have seen Babu come. Babu, take your concoction, okay. Babu. That is very concentrated.
Hey.
Tell the students how you are feeling. No, you are used to this.
I'm now feeling high.
Tibin.
Too cold.
So what Babu has taken is this very concentrated solution, and I took this. So for me to make this solution, 0.001 moles, this is what I have here. That is the moles I need to take from here. So 1 mole is in 1,000. What about 0.001 moles? I'll take 0.001 times 1,000 divide by 1. So I require 1 centimeters cubic. If I take 1 centimeters cubic here, I put it in a combination of this nature. This is 1. I put some water first. Then this is water. Then I put 1 centimeter cubic of that. Then I top up. Then I top up to here. Then this is going to be 0.001. No, not to, this is 500 centimeters cubic. I take this kind of flask, as in this, and I add water, then this is going to be moles per liter. Now, if you look carefully at this work, if you look carefully at this, the molality of the concentrated one was 1 molar. And the volume here of the concentrated one that I've taken is 1 centimeters cubic. Then the volume here, the molality of the dilute one was 0.002. And here the volume of the dilute one was 500 centimeters cubic. This is, so if I multiply this by this, I'll get 1. If I multiply this by this, I'll get 1. In other words, the molality of the concentrated times the volume of the concentrated is giving me the molality of the dilute one times the volume of the dilute one. So this is method number 2. This is method number 1 of determining the volume of the concentrated solution that you require, the volume of the concentrated solution that you require to fetch from here and to make that kind of thing. Let's take example number 2. You have 4 molar sulfuric acid and you want to prepare 2 molar sulfuric acid, and here you want to make for 100 students, you want to make for 10 students each using 10 centimeters cubic, giving you that. So this is the volume you want, but these students cannot use this. It's too concentrated for them. So you want to dilute this solution for this number for 10 students, each taking 10, so you require 100. So how do you go about that? Here we are saying 4 moles are in 1,000 centimeters cubic. Keep that one aside. Method 1 tells us, then we come here. 2 moles are in 1,000. What about 100? You require 2 times 100, 2 times cross multiplication divided by 1,000. This gives you 0, this goes, so 0.2 moles. You require 0.2 moles from here. So 4 moles are in 1,000. 0.2 moles, the one you require, are in how much? This is 1,000 times 0.2 divided by 4. This is simply 200 divided by 4, which is about 50 centimeters cubic. What does this one mean? This means that if you fetch 100 centimeters cubic, 50 centimeters cubic, put some little amount of water, then you put 50 centimeters cubic of acid, and then you top up to the mark of 100, Now, and then you shake. Then you top up with water. This solution that you have here is going to be 2 molar sulfuric acid. Is that true if we use the formula? The formula says MC VC must be equal to MD VD. Molarity of the concentrated solution times the volume of the concentrated solution would give us the same value if you do the product of the molarity of a dilute solution and the volume. So we see this is 4. Here this is 4 molar times VC is what we don't have, should give me 2 molar times 100 centimeters cubic. Now, if I divide here by 4 and here by 4, here we will get VC should be equal to, this is 50 centimeters cubic. Now, would you get the same marks in an exam if you use the 2? Why not? You can use exactly this method and you'll get the same value. The same answer will be the same, and you'll get equal number of marks. And you don't have to really struggle with so many other things and so on. The last but not least, you have 18.4 molar sulfuric acid, what we noted. This acid is as bought from the shops. And here you have your students who have to use 2 molar sulfuric acid. And these students are, you want to use 2 liters, which is for purposes of this lesson, assuming you want to have 1840 centimeters cubic of solution. So simply, we are asking ourselves how much of the concentrated acid will you use? MC VC should give you MD VD. So this gives you 18.4 times VC should give you, the other side is 2 molar times 1840. So if we divide here and here, here we divide by, to get this, we divide by 18.4, and here we divide by 18.4, then this divides with that, then you are left with VC should be equal to this, is that gives you 100. So you require 200 centimeters cubic. What is the implication here? What is the implication? Implication is that you fetch 200 centimeters cubic of this acid, and then you add water to it up to the point you will get that. But remember again, we add acid to water. So you will first have to use your container, whatever container you are using, you put a bit of water, then you put the acid. But of course, you make sure that there is no flask of this measurement. This one we used for purposes of this lesson. But assuming there was, then you top up to this mark. This one we would have used to approximately 2 liters, but then you needed to use this for purposes of, because these are theoretical values, I don't have the values that I'm talking about. Now, from there on, we can move on to what we are saying. How and where do we apply this? This one we apply it when dealing with stoichiometric equations. With stoichiometric equations, we are dealing with stoichiometry. Stoichiometry. This is the relationship. This is the chemistry of the relationship between the masses of the reactants and products in a chemical reaction, resulting in a chemical equation. So in this case, when we are in this study, then we are dealing with the relationship between the masses. For instance, if you have iron, which is 56 grams, combining with sulfur, which is 32 grams, the product you will get will be iron sulfide. If you work out the masses of iron plus sulfur, if you take 32 grams of that and 56 grams of that, the two will combine completely, forming which is 80 grams. The other side of the equation will give us 88 grams. This is simply to say that we are dealing with stoichiometry, and an equation like this one is a stoichiometric equation, giving us the relationship between the masses on this side and the masses on that other side. The number of atoms on this side and the number of atoms on that other side must be the same. And this is why we are dealing with balanced chemical equation. So in stoichiometry, we are dealing with a balanced chemical equation. The number of moles on this other side of each one of them, 1 mole of iron, 1 mole of iron. In this case, we are dealing with 1 mole of sulfur, 1 mole of sulfur. That 2 grams of sulfur, that 2 grams of sulfur. 56 grams of iron, 56, a total of that is balanced. Then the other thing we move to in stoichiometry is talking about state symbols. State symbols. These are the state at which these elements, these compounds are at room temperature. And which are these states? One of them is a solid, symbol S, and in brackets. The other one is a liquid, symbol L. The other one is a gas, symbol G. And we still have another one. When that solid, that liquid, or that gas has been dissolved in water and it is soluble, then we are talking about aqueous, AQ, and in bracket, and written also as a subscript. Subscript means at the bottom. So, and lowercase. In this case, we are dealing with number 1, acid-base reactions. For instance, here we take number 1, A, sodium hydroxide, aqueous. It's a soluble salt. Combining with hydrochloric acid, aqueous. This would give us sodium chloride plus water. Now, for purposes of this lesson, to know the products is very, very simple. Simply write sodium hydroxide and write HCl like that. Let sodium take that and let hydrogen go with that. Sodium and chlorine gives us sodium chloride. Hydrogen and OH gives us water. Now, this equation, this is balanced. Balanced with what? Sodium and sodium, oxygen and oxygen. Hydrogen, there are two. On the other side, there are two. So my equation again is balanced. The state symbols, this is aqueous because it's a soluble salt, soluble salt, soluble salt, and that's a liquid. And therefore, this is stoichiometric. This is stoichiometric equation. We can take another example, and this one is an example of sodium hydroxide also, plus sulfuric acid. You can complete that using that argument of that kind, because this is a base, it's an acid-base reaction. You can have another one. This is sodium oxide plus nitric acid. Now, given this kind of work, given this, you can complete that. Moving on to something else, we can look at reactions that involve displacement. With displacement reactions, very simple, it is a more reactive element displacing a less reactive one from its oxide, its chloride, or its halide, or its compound, simply from its compound. And we can take an example of the halogens. Halogens. And here we are saying foolish, cracks, who blew ink. This means we have fluorine, chlorine, bromine, and iodine. And you can look as, because these are nonmetals, reactivity decreases. Reactivity decreases with decreasing, or rather with increasing, let's start with this, with decreasing atomic radius, or decreasing electronegativity. So in that case, that means fluorine is more reactive than chlorine, which is more reactive than bromine, which is more reactive than iodine. So reactivity decreases like that. This is most, and this is least. So when we have a compound of, say, potassium chloride, and this is combining with fluorine. This is a gas, and this is aqueous. Its stoichiometry means that this combines with this, giving us potassium fluoride. And this is again soluble, plus chlorine is gaseous. the state symbols are correct, then fluorine here are 2, this is 1. So you need to make it stoichiometric, balancing it like that. So our equation is now balanced, and you can see that that reaction is a pure stoichiometric one. If we have now potassium fluoride, you are combining it with the chlorine. Now in this case, you find that fluorine is more reactive than chlorine, and like this reaction moves this. What would happen if we reversed it this way? Chlorine is less reactive than fluorine, and therefore in this case there is no likely tendency of displacement. So what do you write? You write here to that examiner at no displacement. You don't write no reaction, you don't write no change, you don't write nothing happens, you don't know. You simply say there is no displacement in that case. Now from there, after you have finished with this stuff, then we move to something we are calling ionic equation. Ionic equations. With ionic equations, let me check. Ionic equations, we have very many. We have those ones that we are saying acid base reactions. And the first one we have talked about is HCl combining with sodium hydroxide, because they are all the same. The first thing to do is state symbols, and then you write sodium chloride plus water. In ionic equations, you have to write these species. These species, you write them as they would appear in water. So when this one has gone into water, this and this will separate, but will not divorce, separating. By separation, I mean the ions leave each other, but within neighborhood. So this is hydrogen ion, and that is the chloride ion. So they are in aqueous state. The same happens to this. Sodium ions and the hydroxyl ions. And they have separated, but they are in solution. Then you get sodium ions and the chloride ions. But the water being molecular, it's a molecule. The molecules do not separate, so it remains water. What that means is very simple, that the sodium ions on this side of the equation and the sodium ions on the other side remained the same. They are simply not really taking part, they are spectating. So this one, you strike it out and you strike the other spectator. You come to this other one and you check the other side. You discover here there is another spectator and another spectator. And these are the ions we call spectating ions, spectator ions. And you strike them out. These are the players who go to the field only to sit at the gallery and watch. They will never score, neither will they defend. So you take the Leonardo, that is the one, combining with that, the non-spectating ions, and you get water as a molecule. Now, whatever has remained is what, and has charges, is what we are calling ionic equation. Now, in that case and in that vein, you can take yourself other examples of sodium hydroxide with sulfuric acid. Use the same argument. Take potassium hydroxide with nitric acid. 1 minute, I give you 1 minute as I take a sip of water, complete it up, balance it up, and get the ionic equation. Now, the other one that we can take, that one you will finish, and in case you are stuck, this is acid-carbonate reactions. Now, in this case, we are saying we take a carbonate of your choice, and this is sodium carbonate. It is aqueous, it's a soluble carbonate. You are combining it with sulfuric acid. Now, state symbols is aqueous. An acid plus a carbonate, you get a salt. Remember what we said? When you take this, sodium carbonate plus sulfuric acid, it is important ujue which which salt you will form. That one takes that. That one takes that. So sodium and sulfate, you get sodium sulfate. Then you will get H2O plus CO2. Now, CO2 is gaseous and water is a liquid. Now, from is you indicate the ionic form of this. How do you determine that? Any solution or any substance that is aqueous will certainly mean it has been dissolved in water and the ions separate. So here we have 2 sodium ions from here. From our previous knowledge of the stoichiometric equations, then the carbonates and the charges. Remember the charges. Then we have hydrogen ions, and they are 2. And the sulfate. That gives us sodium, and they are 2. And the sulfate here. The state symbol is for all of them. Then H2O, it's a liquid. Then CO2, anything gaseous, anything solid, anything liquid, you don't really touch. You only touch the ones in aqueous state. So sodium ions are on that side, spectating. If you cancel 2 there, you must cancel 2 here. So these are 2 sodium ions. I cancelled with 2. So what was left? Anything else to cancel, class? Certainly not. So here we get the CO2, not the CO2 now, the carbonate ion plus hydrogen ions, and the Al2 will give us water, and again it must balance. So this is the ionic equation. Now, for purposes of your working, you can take calcium carbonate plus HCl. Finish. Potassium carbonate plus nitric acid. Magnesium carbonate plus sulfuric acid. Complete and get the ionic equations for your case. Those are yours for you to consider. Let me see something else. Oh, sorry. I've my cameraman has signaled me. here, sorry. This one should have been a sulfate. Oh, there was a sulfate, so yes, thank you. And the sulfate here. So this one is correct. Oh, I forgot. Thank you, my cameraman. He's doing a wonderful. He has been in some chemistry class. Then from there, we take precipitation reactions. Precipitation reactions. In this case, we can take lead nitrate. I'm combining it with potassium iodide. This is aqueous. Would give us lead iodide plus potassium nitrate. All nitrates are soluble, and then we balance it up. Lead here is 1, lead here is 1. The nitrate, so we balance it up here by 2 and here by 2. So the next thing is to separate the ions. We separate the ions. Lead ions, nitrate ions, and there are 2. Combining it, 2 potassium ions and 2 iodide ions. This one giving us lead iodide. Of course, plus 2 nitrate ions and 2 ions. So the next move is to cancel out. The nitrate is here and the nitrate is up there. Spectating ions. Spectating. Then potassium is here as ion. Potassium is here. So you cancel out the So you can finish up that lead nitrate plus potassium sulfate. Complete it, make it stoichiometric, balance it, put the state symbols, and work out the ionic equation. You can look at barium chloride, combine it with sodium sulfate. You can take barium nitrate, combine it with potassium sulfite. Here the difference is 8 sulfate sulfite. Work out the product for that. These 3, you can get them like that. Then we can go to displacement reactions. Displacements reactions. involving ionic equation. So in this case, we take examples of potassium, potassium bromide. It's a soluble salt. You combine it with fluorine. This one, fluorine is gaseous. Now potassium and bromine, potassium bromide. So when the two combine, this is more reactive than this, and therefore displacement. So we get potassium fluoride, it's a soluble salt, plus bromine, bromine liquid. So in this case, we balance it up. Bromine, bromine, so we put a 2. And fluorine, we put a 2. So we put now the ionic form of it. Potassium is like that, combining with the bromide ions. Bromine in aqueous state, bromide ions, combining with the fluorine gas. And for F for fluorine must be capital, uppercase. You are combining here to get 2 potassium ions and 2 fluoride ions. You would get the bromine as a liquid. So the next move is to cancel out, strike out what is not. That is potassium. So what is left? You get the bromide ions, aqueous, plus fluorine gas. This one you get 2 fluoride ions, which is aqueous, plus bromine liquid. And that is, in that case, the ionic form. These potassiums are the spectating ions. This one and this one have remained unaltered in that reaction. Now, next we can take potassium chloride plus fluorine. Complete that. Sodium iodide plus bromine. Potassium bromide plus chlorine. Now for those three, you use the same argument, and then you will work out the answers to that effect. And by the way, when you are working out ionic equations, it is important you ask yourselves whether the salt is soluble or insoluble. For instance, we know that all nitrates, all nitrates are soluble. All of them. And in that case, the state symbol should be aqueous. And as long as there is water. Number 2, all sulfates are soluble except lead sulfate, barium sulfate, and calcium sulfate, which is sparingly soluble. And we say in this case, pubs and bars in summer. This is something to help you remember this. So this is lead sulfate. This is barium sulfate, insoluble. And these are the sulfates. Then, from there you can have all carbonates are insoluble. So all these ones are solids. These ones are solids in the reactions. All the others would be aqueous. All carbonates are insoluble except NaK, NaK, where N means sodium carbonate, A means ammonium carbonate, and K, potassium carbonate. So all these three are aqueous. They are soluble. All the other carbonates would be insoluble. And lastly, all chlorides. All chlorides are soluble except lead chloride, silver chloride, and mercury chloride. So there's nothing there. So this is solid, it's insoluble. This is solid, this is solid. So we say, this case, publicans, to help you remember. Publicans against having 1 in crabs. So this means lead chloride, silver chloride, mercury chloride are the only chlorides that are, all the others are aqueous, except this. So when you are writing ionic equations, then we are saying you will be good to go. Now for purposes of time, I wish to stop there for our today's lesson, but I want to invite Mheshimiwa to come and wind up for the next lesson's work. Karibu Mheshimiwa.
Thank you very much, Mwalimu. This was wonderful, and I would like to take this opportunity to thank you very much for the lesson. I hope and I know that our students must have enjoyed the completion of the mole lesson. Number 2, I would like to take this opportunity to tell you that next lesson we will be having mathematics, that is KCSE revision. Then after that we will do titration in chemistry. Titration will be practical, and as you can see, I have some of the apparatus here with me. I have a pipette, as you can see here, and on my left hand I have a burette. I have a conical flask with me here, plus a funnel for the experiment, and lastly I have a volumetric flask. So the next lesson we shall deal with titrations. I'm saying titrations because we'll have different types of titrations. That is acid-base reaction, titration on acid-base reaction. We have acid-carbonate reaction. We'll have redox reaction, back titration, double titration, and finally thermal titration. Thank you very much. Until we meet again. Yours truly, Babu Owino. God bless you all. I have some of the few comments that I would like to read to you, and I hope the majority, at least 400 people got airtime today on Facebook. On Instagram, we have Martha Morash. Wallahi leo tumelala kidogo, lakini nimeelewa mambo mingi iko sawa. Jacinta Mbide, Tibim, Niklaus Kamau, wow. Mutesa _KE unasoma mambo iko sawa kabisa. Konge Chris, that's nice Babu. Lucas Roy 98, thanks Mwalimu Gishui. Complex _Mike, the lesson was late Mwalimu Gishui, uko juu kama upstairs za heaven. Hey, hiyo iko noma sana. Now on YouTube, tuko na Berin Otieno, that was a wonderful class. Tuko na Simon Nyangara, good work mwalimu, the world is watching, the power of a pen in your teachings. Thank you very much. Eronia Harun, this is great work. H.E. Babu Owino, this is legit. Mwalimu Gishui, asante sana. Terry Mudoni, thanks, the lesson was beneficial. Nice lesson. Blaze, fantastic. Kaula Hamed, thanks Babu for the class. Na tumeshukuru mwalimu sana. On Facebook we have Kennedy. Babu kijana ni kijana kwa sababu kama kuna tabu ana jawabu la ajabu. Hiyo ni Tibim. Alex Musioka, good work. Honorable Mazee, imeweza iko sawa. Na namwambia ndini. Tuko pamoja kabisa. Richard Onditi, how amazing. This is a good job. Harun Oromo, Chonjo, Abdira bin Kadir. Babu, tufundishe pia law. Law ntawa handle. I'll see what to do in law. I can handle family law. We talk about testacy, intestacy. We talk about divorce, if you want to divorce, and I won't advocate for it. And we'll talk about different kinds of marriages. Some of them are potentially polygamous, while some, like the potentially polygamous, we have marriages like the Islamic marriage and also the customary marriage, while the civil marriage, Christian marriage, and civil Christian are majorly monogamous marriages. So Dan Kimesh, class. Rangila Kokumu, content iko juu. Momanyi, it was wonderful. It was a wonderful class. Kezi, all the way from Uganda, we love this. Edward from South Africa, we are watching this and sharing with our kids. Lavender, this is YouTube. Can't see it. Lavender Jeb Korir. Hey, Professor Babu Owino, thank you for the lessons that you offer. I'm from Limuru Girls. The lessons are really helpful. Be blessed. I'll communicate. You've left your number here. I'll communicate. We'll ensure that you go to the university. You guys subscribe to our YouTube channel. That is Babu Owino TV. Mambo iko sawa. Naona somebody all the way from Washington DC. Hii lazima tuambie Trump kazi ipangwe. Usiniite kwa hiyo demonstration, itakuwa noma. Huska Bobby, I really love it. Mambo imekuwa sawa. Simon Ratemo, kazi iko proper kabisa, asanteni sana. Harun Oromo, watching from Kayole Matopeni, huyo ni mtu wako Tibim. Haji Babu teaches biology. Biology hapo tutaleta wana biolojia, mambo itakuwa sawa. Although biology is easier than even mathematics and chemistry, so it will be so easy. Thank you guys. I hope kila kitu iko sawa and you enjoyed your class. Till we meet again. Thank you and God bless you all.